Okay, so I'm going to finish the material about using energy methods. So the problem I'm going to solve here actually is in the book. It's Centuria section 10.4, and here's the pages that it's on. And so the idea is that when we have, mostly when we talk about spring constants, so far we've been treating the springs like they're linear, and it turns out that at large deflections, springs often stiffen. So a linear spring we could write as like, we read it basically as k times, and I'm going to call it, sort of reluctant to call it, let's just call it k times y for now, okay? Because when we defined it before, we had y, so x is basically the distance along this direction here, and we have y of x here as this deformation function. So at large displacements, then f spring, this is linear, right, because it's basically constant times y, so this is the equation for a straight line. At large displacements, we may get k times y plus like some k prime times y to the third power plus some k double prime times y to the fifth power. Right, so this is now some polynomial expression. So this is clearly not the expression for a straight line, right? It's the expression for a polynomial. And this may not be the exact expression for every spring, but anyway, when the deflections are large, the spring constant may not be, we shouldn't really think about it as a single spring constant. So now let's derive what this is for a clamp beam. This is a case that's pretty important in MEMS. And so what we've drawn here is basically it's clamped at two sides, and it has some length to it, L. And the way that this x is parameterized is basically we set it up so that this is x equals 0 here, and this is x equals plus L over 2 here, and this is x equals minus L over 2. Okay, so sometimes we'd set x equal to 0 on the left-hand side of the beam. We integrate from 0 to L. In this case, we're going to look at starting at x equals 0 in the middle. And one of the reasons why we might do this is because this is actually a symmetric problem, so we can sort of look and see that the deformation shape is identical on to the left of x equals 0 and to the right of x equals 0, and so that means that we can integrate possibly over just half of the beam. And what this is showing here, there's a force applied at a point in the middle of the beam, and this dashed line is kind of meant to show what the mode shape looks like. And here what it's drawn is the mode shape is y of x, and I guess so we'll call this guy the y coordinate. What I did was actually in the notes later on, I'm going to call this u of x. Okay, so that's the deformation shape. I'm not going to call it y of x because I found that to be a little bit confusing, and in particular when I was using MathCAD, it was problematic to have more than one thing named y, right? So this is the y-axis here. And if you remember, we defined the beam as having some height like this. And similarly to what we did for the x-axis, I defined basically, if we think about the beam direction here, I said y equals 0 is the neutral axis, and then this is y equals h over 2 here, and this is y equals minus h over 2. So this is my picture of a slice of the beam, okay? So you'll see integration where I integrate from minus h over 2 to h over 2. So I've done the same thing. I basically split the beam in the middle in the y-axis, and I split the beam in the middle in the x-axis. The other thing I'm going to say is, so the dimension that we have, so we have h is the y-axis dimension, L is the x-axis dimension, and we said basically b is the z-axis dimension. So this is like the width into the page. Okay, so those are the definitions that I used in the previous lecture, and so I'm trying to be consistent with those things. And let's see, what more do I want to say about this? Okay, so let's look at, if you remember, now when we think about the spring constant for this thing, when I calculated the spring constant, what I really want to know is this is actually like f equals k times y. We're actually calculating for some point deflection, and here we have this function u of x. And so what I'm going to do is if we look at, I need to expand this a little bit. So we've got u of x as some function. We're going to say u of x evaluated at x equals 0. That's the deflection at the center of the beam. I'm going to call that u naught. Okay. And so in the linear spring version of the world, linear spring constant would be F spring is equal to the spring constant K times U of 0, okay? U sub 0, U naught, is the deflection of the beam. And we could really think about that as the amplitude of this, this mode shape, okay, or this deformation shape. So I could call this, this is U naught, okay, deflection at beam center. And so I want you to internalize this idea, right? Normally we say like F equals K times Y or something. So U naught is our displacement amplitude that we're interested in terms of the spring constant. So later on, if we made a lumped element model for this thing, we would use U naught as the displacement of the beam. So let's go a little bit further. Okay, so the principle of virtual work. So I'm going to assume a trial function that satisfies the boundary conditions. So I'm going to write u of x is equal to 1/2 u naught times 1 plus cosine 2 pi x over L. Okay, so how did I pick this? Well, if I look at the shape of this beam, it kind of looks like a cosine function to me, right? It sort of has 0 slope at the boundaries, which is what it should have because it's clamped there. So the slope should be 0 here. And it's varying in this sort of cosinusoidal fashion here. So it has a peak in the middle, and it has 0 amplitude at either side. And if you remember, right, the cosine, let's see, do I get the right answer here? So at, yeah, and so if we think about it, is if we calculate at x equals minus L over 2, then cosine of 2 pi x over L is going to be equal to cosine of minus pi, and so that's minus 1. And similarly, at x equals plus L over 2, we get cosine of plus pi, and that's equal to plus 1. I'm sorry, minus 1. And at x equals 0, we have cosine of 0, and that's equal to 1. Okay, so if you look at this thing that's in the brackets, we could see that u evaluated at 0 is going to be 1/2 u naught times 2, or it's going to be u naught. Okay, so that's why we end up with this factor of 1/2 in front of the whole thing. And you could see that basically the thing in brackets going to evaluate to 0. So you can see that u evaluated at I'm going to write it like this: u of x at x equals L over 2, or at x equals minus L over 2 is going to be equal to 0. Okay, so it does indeed satisfy those boundary conditions, and without proving it, if the other boundary conditions that we have for this beam is that the slope has to be equal to 0, so the derivative of u of x evaluated at minus L over 2 and plus L over 2 has to evaluate to 0. I'm not going to do that here, but I will assert that it is true. Now, if we consider only the bending energy, so we could go through the same calculations that I did in the last lecture, and if we consider only the bending energy when we evaluate our strain energy, then we're going to get actually a linear spring constant. Okay. So our potential energy function is going to be U is equal to the strain energy minus F, the work done by the external force. And let's look at how we want to do this. Well, the force is applied at the beam center, okay? And so the displacement that this is acting on is U naught. Okay. And then what we're going to do, and so W here is the strain energy. if we consider only W equals the bending strain energy, then what we'll get is eventually we're going to get a linear spring constant. Okay, and I should say that what we're going to do is we're going to basically evaluate. If you remember, the way that we do this is we have a trial function that is parametrized. And so let's look at our trial function here. I'm going to put it in a red box. Okay, there's only one parameter here, right? The other stuff is we know the beam length. The only parameter here is u0. So this is a one-dimensional function. And so when we calculate, when we use this, how do we use the potential energy function? Well, we're going to do du naught. Okay, so we're going to take the derivative of this energy function with respect to the displacement at the beam center equals 0, and we're going to solve. Okay. All right. Now the difference is here we're actually going to account for the fact that if we look at this beam, this deformed shape, clearly you can see that the deformed length of the beam is a lot longer. So it's been stretched out, okay? And that stretching of the beam results in an axial tension force. So as I push the beam away from its neutral point here, I'm increasing the tension in the beam, and so I have to account for that tension. And in mechanical engineering, we talk about that tension as being basically an axial strain. Okay, and if you remember from the previous lecture, so I'll just say basically like this. Now we're going to account for an axial strain. And if you remember from the previous lecture, I said that the axial strain is equal to 1/2 du dx squared. Okay. And I should be careful. So this is basically the axial strain at a point along the beam. Okay, and I'll be a little bit more careful here too. Okay, so the axial strain at a given point, we can find that by evaluating the slope of the trial function and squaring it and then dividing by 1/2. Okay, so this is in the previous lecture. I did make a mistake in the previous lecture. So the way we're going to account for this axial strain, so this is the axial strain at a point x. Now what we need to do is to find the total axial strain. It's the integral along the length of the beam. Okay, so we're going to integrate this strain along the length of the beam. And one thing that's a problem about writing the integral this way is what we'll end up with if you imagine that this, let's say that this little EA as a function of x, if it was a constant, well, when we integrate this, we're going to get L, and you know, right, because the integral over minus L over 2 to plus L over 2 will evaluate to L if this is a constant. And the strain is the delta L over L, so I need this extra factor of L here, okay, when I do this integration. Okay, 1 over L times the integral along the length. So this is the total axial strain, and this is what we need to calculate. And I'm going to continue along here in just a minute. So I'm going to stop the video and I'll continue after the break.